For problem 7.134, we have an emitter follower circuit, okay, and it's given that beta, it can vary from 50 to 200, okay, so from 50 to 200. The circuit is this one here, and we need to find the emitter current, the emitter voltage, and the base voltage. So first we are going to start with a DC analysis, and for the DC analysis, those capacitors, they become an open circuit, right? This one here too. And basically we can ignore V signal and 10K here on the left side of the circuit, so this part here it's detached from the circuit, and this one here is also detached from the circuit. So we're left with this 100K here, this 1K here, and this 3 volts at this point here and that point there. Okay, so now that we have this simplified circuit, right, just this green part here, we can start doing a DC analysis. So first thing is that we know that VC is equals to 3 volts, right? And we can also assume active mode operation, so that VBE, because it's a NPN transistor, is equals to 0.7 volts. Okay, now from that we can apply a loop analysis at the base. So basically here, right, we go up there and then go back here. So we start with those -3, so let me use blue here, so -3 volts from this voltage source plus IB times 100K ohm. And then remember that here at the, so let me draw down here, so here we have 0.7 volts, so it's plus 0.7 volts plus the emitter current times the emitter resistance, which is 1K, and that should be equals to 0, right? That's the equation. Now remember that for active mode operation, the base current is equals to IE divided by beta plus 1. So we can substitute this equation here for beta, for base current, and then we can isolate IE, right? So IE is equals to 2.3, those 3 minus 0.7 on the right hand side, divided by the emitter current, the emitter resistance 1K, plus the base resistance 100K, divided by beta plus 1. Okay, now because beta varies from 50 to 200, we are going to get a range of emitter currents, and this range, it goes from, so if we substitute beta here as 50, we get an emitter current that is equals to 0.78 milliamperes, and if we substitute 200, we get 1.54 milliamperes. Okay, so those are the currents for the emitter based on this range of beta. So now that we know the emitter current, right, we know the current that's flowing through the emitter here, we can calculate VE. So we know that VE is equals to the emitter current times the emitter resistance, 1K ohm. And this gives us also two values of VE, one for 50 and another one for 200, right? So the values of IE changes as beta changes. So for 50 we have 0.78 times 1K, and that gives us 0.78 volts. And for 200 we have those 1.54 milliamperes, that gives us 1.54 volts. So this is for VE, right? Now, because we assumed active mode operation, we know that VB minus VE is equals to 0.7. So again, VE changes because IE changes. So VB is equals to VE plus 0.7 volts. And because we have two different values for VE based on the value of beta, we get two values for VB. So VB is equals to, for 50, beta equals to 50. 0.78 plus 0.7, so it's 1.48. And 1.54 plus 0.7, that's 2.24 volts. So that's VB. Okay, so we find out IE, VE, and VB, which was the unknowns for part A. Now for part B, let me go down here a little bit. So for part B, we need to find the input resistance. Okay, so the input resistance. So find the input resistance, and we can use the T model for that. Okay, so the T model, and that's what I have here in this circuit. So if we substitute this first, right, because we are going to perform a small signal analysis, now this capacitor becomes a short circuit, this capacitor becomes a short circuit, this one here and this one here, they both go to the ground, right? So we can substitute the BJT here by its T model, and the T model, if you remember, is the voltage, the current source, and the small emitter resistance. So this is the collector, this is RE, this is what I'm calling VBE, so this is GM times VBE, this is the base, this is the emitter, right? And we know that RE is equals to the thermal voltage divided by the emitter current. And again, the emitter current, it changes with beta. So this gives us two values of RE depending on the value of beta. So for 50 here and 200 here, RE is 25 millivolts divided by 0.78 milliamperes. So it gives us 32.05 ohms for beta equals 50. And for beta equals to 200, we have 25 millivolts for VT divided by the emitter current, that's 1.54 milliamps, and that's equals to 16.23 ohms. Okay, so the values of RE change. Now, if we look at the, well, there's a chapter in the book that basically gives us, it gives us this input resistance. So if we look at this from this terminal here, this is R in 1. That's given by the book. So this R in 1 is equals to beta plus 1 times RE plus RL. And for that particular circuit, RL is just 1K, or just the load resistance here, because usually the emitter is grounded. But in our case, I mean, for us it's not the case. So our load is actually this entire thing here, which is the parallel between 1K and from the emitter resistance. So if we look at here, this 1K here, it's not grounded, right? So we have the parallel between those two Ks. So this is R in 1. And if you look at the, if you want to determine this R in here, which considers the base resistance, this R in is actually R in 1 in parallel with the 100K. Okay, does it make sense? We have those two here that makes our load for this equation. So we add this load here, so it's a series, right? RE plus RL. But here RL is a parallel between 1K and 1K. So this one here plus this parallel times beta plus 1, that's the input resistance seen from this terminal. But we want to figure out what's the input resistance seen from this terminal here. And that's R in 1 in parallel with the 100K, right? So first, RL is equals to 1K in parallel with 1K, and that's half of 1K, right? Because it's 1K times 1K divided by 1K plus, plus 1K. So the load resistance is 0.5 K ohms or 500 ohms. Okay, so we can calculate R in, and our R in 1, well, I'll leave it that way and then I will just write the final equation. So if we expand this equation here, we know that R in is equals to R in 1 in parallel with 100K, so that's 100K times beta plus 1 times RE plus R load divided by 100K plus beta plus 1 times the small signal emitter resistance plus the load resistance. And this, if we substitute the values of RE, remember we have two values for RE depending on beta, right? If you go back here, two values of RE. So this gives us an R in that's 21.3 kilo ohms for beta equals 50 and 50.9 kilo ohms for beta equals to 100. Okay, and the last part, let me see if I have it written here, so I don't, but the last part is part C, that asks us to determine the voltage gain. So find V out over V signal. Okay, and one thing is that if we look at, so this is basically, this is VB. Okay, and for the signal resistance we have 10K. So this is 10K. Now we can obtain a relationship between VB and V signal because we call this entire thing here as the input resistance. So if we look at this loop here, we can obtain a relationship between, so let me draw here, V signal and VB here using a voltage divider, right? So VB is equals to V signal times the input resistance, because that's the resistance that we have here, the overall resistance, divided by the input resistance times the source resistance, that's 10K, the signal resistance, that's 10K. Now if you remember, R in is also dependent on beta, right? It has two values. So if we isolate VB over V signal here, we get two answers, okay? One for 50, one for 200, based on these values here for R in, okay? Input resistance. So if we substitute the values of R in this equation here, okay, we get the ratio VB over V signal as 0.6805 volt per volt, and 0.8357 volt per volt for beta equals to 200. And now we can establish a relationship between VB and V out. So if we know that this VB here, right, this VB here, it's just a matter of applying a voltage divider between RE and this parallel here, because this here is V out, right? So if you know that at this node here we have VB, right, because it's the same node, we have part of VB is applied through this RE, and part of the VB is applied through this parallel between 1K and 1K. So we can write an equation that V out is equals to VB times, now V out is the voltage across the parallel between 1K and 1K, and we know that is 500. So it's times the 500 using the voltage divider, 500 divided by 500 plus the meter resistance. And again, this term here, it changes for values of beta, right? So at the end we have, so let me just show you up here. So remember that RE here, it is 32.05 for beta equals 50 and 16.33 for beta equals to 100. So for V out over VB, right, isolating those two terms here, that's equals to 500 divided by 500 plus the meter small signal resistance. And this gives us two answers, okay, one for 50, one for 200. Now if RE is said to be 3205 for beta equals 50, we get V out over VB equals to 0.94 volt per volt. And for 200, which is RE equals to 16.23 ohms, that's equals to 0.969 volt per volt. Okay, so that's VO over VB, and that's VB over this signal. Now if we take VB over this signal times V out over VB, that actually is V out over this signal, right, because this cancels with that one. So if we take this one here, multiply by that one there, we get the voltage gain, the overall voltage gain for beta equals to 50. And if we take this one here and multiply by that one there, we get the overall voltage gain for beta equals to 200. So this one here is equals to 0.6805 times 0.94, which is 0.64 volt per volt. And the second one is 0.8357 times 0.969, and that's 0.81 volt per volt. So that's the final answer for part C, especially this one and that one. Okay.